Okay, so today we're cracking open the secret playbook that pretty much every scientist lives by. And I'm not talking about a bunch of boring rules. This is the shared language they use to build on each other's work and turn, these wild ideas into actual world-changing discoveries. If you're in an intro to chemistry class, this is basically your cheat sheet for chapter 3. All right, let's get into it.
I mean, this is the big one, isn't it? How does a single little spark of curiosity in one person's brain eventually turn into something that we all just accept as true? Well, it's definitely not magic. It's a process. It's a journey that takes communication, a ton of testing, and a whole lot of trust.
Just look at the atom. Way back around 400 BC, this Greek philosopher Democritus came up with the idea that everything was made of these tiny, uncuttable particles he called atomos. It was just an idea, right? A total guess. But because he shared it, thousands of years later in 1803, a scientist named John Dalton could pick up that same idea, actually test it, and build the first modern atomic model. And ever since then, we just keep learning more. It just goes to show you, science is a team sport played across centuries.
So, how do scientists talk to each other across all that time and space? Well, they use a universal format. Now, try not to think of this as some boring homework assignment. Think of it as the official way to tell a scientific story so that anyone, anywhere, can understand exactly what you did and why you did it.
And every good science story follows this exact same path. It all starts with the purpose. That's the big question you're trying to answer. From there, you make a hypothesis, which is really just your best educated guess about what's going to happen. Then you've got the procedure. That's your step-by-step recipe. After that comes the fun part, the data and results, where you show what you found. And it all leads to the grand finale, the conclusion, where you explain what you actually learned. See? It's a perfect, logical flow from question to answer.
But here's the thing. You can follow that story structure perfectly, but what if your data, which is kind of the star of the whole show, isn't perfect? Because in science, just getting an answer isn't good enough. You have to know how good that answer is. And that brings us to this really important difference between being right and just being consistent. And that brings us to two of the most important words you'll ever hear in a lab: accuracy and precision. It sounds complicated, but the difference is actually super simple. Accuracy is how close you get to the real, true answer, the bullseye. Precision, on the other hand, is just how close your measurements are to each other, even if they're all wrong. And here's the kicker. You can totally have one without the other.
The dartboard analogy makes this whole thing click. If you hit the bullseye every single time, you're both accurate and precise. That's the dream. But let's say all your darts land in one tiny, tight little group way over in the corner of the board. Well, that's incredibly precise because you're consistent, but it's not accurate at all. The goal in the lab and in all of science is to be consistently correct.
So if the goal is that perfect bullseye, what happens when we miss? We talk about it. We report it. You see, in science, the word error doesn't mean you messed up or you failed. It's really just a measurement of how uncertain you are. Being honest about your errors is actually how you build trust with other scientists. It's not about being perfect. It's about being totally transparent.
And it turns out, not all errors are the same. They pretty much fall into two big categories. The first is systematic error. This is a consistent, repeatable problem, usually with your tools, and it totally messes with your accuracy. Then there's random error. That's just the unpredictable little variations you get when you measure things, and it's what messes with your precision.
Okay, here's a classic example of a systematic error. Imagine your digital scale isn't zeroed out properly, and it starts at 0.02 grams. Well, that means every single thing you weigh is going to be exactly 0.02 grams too heavy. It's a consistent problem that throws off your accuracy in the exact same way every single time. And we've all experienced random error. You step on a bathroom scale, right? And the numbers kind of flicker back and forth a little. Is it 150.1 or is it 150.2? That tiny, unpredictable little jump, that's random error. It's just the natural noise in the system that affects your precision and makes it tough to get the exact same number twice. This is why it's so important to remember this. Reporting these possible errors isn't just a good idea, it's a requirement. It's a scientist's way of saying, look, here's what I found, but here are the limits. Maybe it was a windy day when I took my measurement, or maybe my scale wasn't perfectly calibrated. That kind of honesty is what makes science so reliable. So scientists don't just kind of vaguely talk about errors. They actually measure them. They use math to put a hard number on how confident they are in their own data. Let's take a quick look at how they actually calculate that confidence and build trust in their results.
One of the most clever tools they use is something called significant figures, or sig-figs, and it's basically a secret code hidden in how you write down a number. So writing down a measurement as 2.75 centimeters instead of just 2.7 tells another scientist that your ruler was more precise. The more numbers you write after the decimal, the better your tool was and the higher your precision.
But really, the ultimate report card for your experiment's accuracy is percent error. It's a really simple calculation that gives you a percentage telling you exactly how far off your result was from the known correct value. A really low percent error basically screams, hey, I was super close to the bullseye.
And figuring it out is a really simple three-step process. First, you just subtract the real accepted answer from the answer you got in your experiment. Then, you divide that result by the real answer just to see how big your error was in comparison. And finally, you multiply the whole thing by 100 to turn it into a percentage that's easy for anyone to understand.
So in the example from our source material, the student calculated their percent error and got just 0.14%. Wow, that is incredibly low. A number like that is basically shouting, this result is super accurate and you can absolutely trust it. It's the numerical proof that you did a really, really good job. So now that you have this playbook, you're not just a passive reader of science anymore, you're a critic. You can look at any study and start asking the same kinds of tough questions a real scientist would ask. Was the procedure followed exactly? What were the possible errors? Does the data actually support the conclusion? You now have the tools to think like a scientist. But that brings us to one last, really important question. What happens if you do everything right? You follow the procedure, you measure carefully, you calculate your error, and your results are just a total mess. They don't give you a clear answer at all. Does that mean you failed?
No way. Absolutely not. In science, getting an inconclusive result isn't a failure. It's a clue. It's a signpost pointing you in a new direction. It's basically an invitation to tweak your experiment, come up with a new hypothesis, and ask a better, smarter question. It's never the end of the road. It's the real beginning of a new discovery.